Okay, in this video we'll be discussing aldols and aldol condensations. So when two molecules of an aldehyde or a ketone react in the presence of a base, they form beta hydroxycarbonyl compounds. So if we take two copies of acid aldehyde and react that in the presence of hydroxide ions with water at just 5 degrees Celsius, so we do this reaction on ice, then the compound that we get will be this. And that it has this alcohol beta to this aldehyde. And remember that this will be our alpha carbon, this will be our beta carbon, and we call this structure in aldol for alcohol or aldehyde and alcohol. So aldol. The mechanism for this reaction will show that. Again, we'll start with acid aldehyde, and we'll show the protons on this carbon because the hydroxide will act as a base and pull one of those protons off that carbon. So the electrons will come up and kick up onto this oxygen and form the enolate. So again, we'll use it would form this enolate, and this enolate then attacks another copy of the acid aldehyde at the carbonyl carbon. So the electrons from this negatively charged enolate oxygen come down, and the electrons in this double bond are kicked over and attack that carbonyl carbon. Then finally we can protonate this oxygen by reacting that with a molecule of water. And we arrive at our aldol product. Now, this aldol reaction exists in an equilibrium with hydrate formation. We have to remember, though, that hydrates are rare, but the equilibrium between hydrate, aldehyde, and aldol depends on the molecule's structure and the reaction conditions. We should also see that aldols usually dehydrate. So again, if we start with the aldol product from the previous reaction, in the presence of a base and water, that will wind up with this product here. And this will be the aldol condensation product, or the aldol condensate. The mechanism for this reaction is that we have these alpha protons here. So again, at the alpha position, we have a hydroxide ion acting as a base, pulls off one of these protons. The electrons move up to form a double bond, and it kicks off this OH as a hydroxide leaving group. In that, hydroxide is an acceptable leaving group because we're in basic conditions, and so we're simply replacing one hydroxide with another hydroxide. And so when we kick off that hydroxide leaving group and form this double bond, we wind up with our dehydration product, or our aldol condensation product. And again, this aldol condensation product exists in equilibrium with the aldol product. And so, and the aldol exists in equilibrium with the aldehyde and the hydrate. And so, when we're dealing with aldehydes, we're actually dealing with several different equilibria. That on one end of the spectrum, we have the hydrate. We have the aldehyde. We have the enolate. We have the aldol. And the aldol condensate. And so, if you're given a question with an aldehyde and basic or acidic conditions, and we'll cover the acidic reaction next, that the most likely answer for the reaction product will be the aldol condensate, because aldols usually dehydrate to form that condensate. If it's a multiple choice exam and the aldol condensate is not given as an option, then look for an aldol. But the most likely answer is that the equilibrium will go all the way to the right, and we'll get an aldol condensate. And particularly if we add heat, because adding heat will force the dehydration from aldol to aldol condensate. So as I had mentioned just a moment ago, that this aldol formation works under acidic conditions as well. So we'll take a look at the acidic reaction. In fact, it will almost always be a condensation product. It will react acetaldehyde again with hydrochloric acid and heat, and will arrive at the aldol condensate. The mechanism for this is that will protonate this carbonyl oxygen with a molecule of HCl. Once protonated, then a molecule or an ion of chloride can deprotonate one of the alpha protons. We can kick the electrons up to that oxygen, and this will form the enol. So rather than the enolate, we get the enol. But the electrons on this oxygen can still move down, force this double bond electrons to attack the carbonyl on another molecule of acetaldehyde. And we would arrive at let's just go ahead and say that that's a protonated acetaldehyde. So we go through this protonation step twice, and we're having the enol attack a protonated acetaldehyde. And so we get this protonated aldol product. Then to do the dehydration, essentially we have a proton transfer. We deprotonate this carbonyl. And we protonate this hydroxyl. And once we do that, we get this species, and our base can pull off one of these alpha protons. We move the electrons from this carbon-hydrogen bond up, and we kick off that water. And finally, we arrive at our aldol condensate. So you go, here's aldol and aldol condensate. So the acid catalyzed mechanism involves starting with the aldehyde. We protonate the aldehyde, then we form the enol. The enol attacks another copy of the protonated aldehyde to form the aldol, well, a protonated aldol. We deprotonate one end and we protonate the other end to form this other protonated aldol, and then we dehydrate through an E2 elimination to form the aldol condensate. So again, this aldol condensate will be the major product that you should look for. An aldol condensate product on an exam if you're given a question about the aldehydes or reacting under acidic or basic conditions. And again, if you can't find an aldol condensate structure, then look for an aldol. So we can do this not just with aldehydes, but we can do this with ketones too. But the equilibrium for ketones is not favored. And so we have to use special lab equipment in order to make that reaction work. That lab equipment is a Soxhlet, it's an L, Soxhlet extractor. But anyway, if we're using a Soxhlet extractor, it is possible to make this reaction work, even though the equilibrium isn't favored. If we start with this ketone, we react that using hydroxide in water, then we'll form this enolate. This enolate will react with another copy of the ketone to form this aldol, and that is in aldol we have the it's a ketone and hydroxyl ketone and an alcohol, and that alcohol is beta to the carbonyl, and then it would dehydrate to form this aldol condensation product. And I should point out that one of the reasons that this is favored is because we get this conjugated double bond system in aldols, or when we convert the aldol to the aldol condensate. But with ketones, the equilibrium is going to favor back towards the ketone, and so the Soxhlet extractor helps to remove this product from the reaction slowly as it goes, and so we can slowly drive the reaction towards the aldol condensate because we're pulling this out of the reaction over time. So that's an introduction to the aldol condensation and aldol reactions.